one of the most striking buildings in the world. In its short life, its distinctive shape has made it an icon for Dubai. Recognized the world over. It's the Burj Al Arab, or Arabian Tower.
This is the tallest atrium in the world, 182 meters high. And that's just the beginning of the superlatives in one of the most opulent hotels in the universe. There's enough gold and marble in here to make a rapper look dowdy, but behind the bling are some truly remarkable engineering achievements, and they wouldn't have been possible without
the children's game of jacks, an engine cam, the pages of a phone book, a revolution in fire hose design.
Look at that!
And a camera flash.
I've seen your point that it's a potential problem. You don't usually see this bit, but this is how I start every day's work. This is how we do things.
Arriving by helicopter is par for the course here.
Thank you.
I'm only doing it to blend in as I'm about to check in.
Why not? Thank you.
To check out one of the most distinctive architectural achievements in the world.
Lovely. Thank you. Would you like some Arabic coffee? I'd love some, thank you. Cheers. Inside, the suites really are luxurious cocoons, sheltering you from the desert outside. There really is no sand in here. Unless, of course, if you really wanted, I'm sure room service could oblige. And then, whilst your bags are being unpacked for you, somewhere in your vast suite, you can stride around and look out over the whole of Dubai. But perhaps, as importantly, the whole of Dubai can look back at the hotel. Because this place was designed right from the start to be an icon.
In the last 20 years, Dubai has shot upwards and outwards, looking to find its fortune through business and tourism. Oil was discovered in the early 60s, but people here know it won't last forever. The iconic Burj Al Arab is part of Dubai's planned future after oil. The architects on the project, however, were inspired by Dubai's past.
Once upon a time, Dubai's wealth came from the sea, where they harvested pearls. And this building's distinctive shape recalls that history. That curve is inspired by dhows, the traditional sailing boats that applied these waters since ancient times.
Making an iconic building look like a ship was only part of the challenge. The architects wanted something more. They needed a statement.
Solution? Well, put your building 300 meters out to sea on its own, tailor-made private island. Because it's not going to be cheap or easy.
Engineers had to make an island big and solid enough to hold a 250,000-ton tower. Most of all, they had to protect it from the sea and the power of the waves. Even this placid-looking gulf can have a dangerous temper, which could easily wash away a man-made island. Back in the UK, I'm going to attempt to show how even a relatively small amount of water can do a surprising amount of damage. I'm going to create an artificial wave. The man in charge of sea defences at the Burj Al Arab was Mike McNichols.
And these things can be pretty powerful.
Yeah, you know, in the right circumstances, at the right speed, they can just act like a solid.
Yeah.
Smashing into whatever's there.
This plate glass will test the destructive power of our wave. And don't think that this glass is a pushover. It's 10 mil thick. It's the safety stuff they use in tall buildings to stop people falling out. It's more than twice as thick as normal window glass. This is going to represent our wave. It's a ton of water. But it needs one more thing to be like a true wave.
You need some, you know, a bit of speed to get this thing going, just like a wave, pushing through the air.
Our wave will be set in motion by gravity and explosives.
What I've done, you'll like this, it's very subtle, is at the bottom of the bag is sort of a loop of det cord, explosive, which will explode immediately. And at that point, there'll be no bottom on the bag, so all of this water, the whole lot will just fall out in one big solid lump. And that's more like a wave.
That's more like it, Richard, yeah.
Well, to complete this demonstration of the power of a lump of water, I've got this. It's a sort of industrial dining table with a glass top, to give it its full title. What'll happen is we'll position the bag above there on the crane, fire the explosives, bang, no bottom in the bag, all of the water comes down in one go, onto there, and, well, we'll see what happens. Part of me thinks even in a solid lump, the water will get here and then just sort of pour around the sides, and the biggest problem we'll have is a puddle.
You'll see. It's going to punch through that glass.
All right. Well, I'm going to make a suggestion. Whatever happens, let's watch it from over there.
Now, I've always thought of water as kind of soft stuff which flows around things. Sure, in a high-pressure jet it's good for cleaning the car, but a cubic metre of it falling onto thick plate glass?
Ah! The box. Really can't hear a thing there.
Nice loud countdown.
Sorry?
And then nice loud countdown and press the button.
OK, right, I'm going to do this. This is it, for real. Here we go. Here comes a wave. Stand by. In 5, 4, 3, 2, 1. Well, there was quite a big bang. Thank you for the big bang. That's really... Well, you can see the thickness of the glass now. It's 10 mil thick. You can stand on that.
Our ton of water only fell a couple of metres, and it still had huge destructive power. Compared to the power of the waves in the Gulf, however, it is a drop in the ocean. The biggest waves that batter the artificial island can deliver hundreds of tons of force. Each wave can be the equivalent of 130 small cars crashing into it. So how do you protect your island from the extreme forces of the waves?
I think we'll take our inspiration, Richard, from this little group of jacks.
So these are jacks. Now, forgive me, but it seems like quite a leap, because how do they take the energy out of the wave?
Well, this is more a modern version of the jack. These things interlock together.
So the principle here is these shapes interlock.
And the space between them, the water swirls within them and loses its energy.
So it's these holes
It's the
that are
holes
doing
that
the
key.
work.
Yeah, the holes. It's nothing creates something.
Holes are the answer. Well, sort of. Holes were first used in revolutionary jack-shaped sea defences created by South African harbour engineers. They saw a local version of jacks being played and, fascinated by how the jacks interlocked, successfully redesigned the harbour defences for East London. Almost all coastal defences still rely on this idea of holes, including the Burj Al Arab. I'm creating a furniture protection system inspired by the sea defences used to protect the hotel, in which spaces are the secret ingredient. Instead of trying to stop waves dead with a wall, the idea was to create a series of spaces, holes, that absorb the energy of the sea. And we're going to see if the same principle will protect my spare dining table.
It will be the holes doing the work, I hope. We need to clear off out of the way. And let's do it again, only this time, my table will survive. Probably. It's your theory.
I know.
Our homemade defences will use the holes in the tyres to redirect the water. It will swish around and should fall harmlessly at the bottom.
All right, I have every faith.
Let's give it a go.
If we've done our homework right, this will save the glass, just as it saves the Burj Al Arab's man-made island.
If we're ready, in 5, 4, 3, 2, 1. This is one of those occasions when just from seeing something you suddenly really understand it, because you can see the breakwater break that big lump of water up into just eddies and swirls and bits. And it really was the holes doing the work.
The holes did all the work. Net effect, a protected table, a protected island, a protected hotel.
Not that my table isn't important.
In Dubai, the Burj Al Arab engineers used exactly the same principle for breaking up waves, except they used concrete, not old tyres. Their defences create a smooth, elegant and uniform shape, suitable for keeping a world-class hotel's head above water.
The holes are so good at taking the energy out of waves that the island could be built at just 7.5 metres above sea level.
Keeping the island relatively low allows the architects to continue the illusion of a boat on the water. But what I think is fascinating is how the architects completed the boat itself inside the sea defences.
Those are just the outer shell of the island. They needed to fill the middle in with something, and they chose sand. Now, I guess it's not like it's in short supply around here, but call me old-fashioned. I've never thought of sand as the ideal material to make firm foundations for a building, especially one that size.
The Burj Al Arab is 321 metres high, slightly taller than the Eiffel Tower. How does it possibly stand on sand without keeling over in the first stiff breeze? Through a remarkably simple scientific principle, in fact.
Skin friction is, well, it's exactly what it sounds like. It's the friction between the skin, the surfaces of objects. If I rub my hands together, friction generates heat. I can feel it. Now, ordinarily, skin friction is, it's there, but it's pretty easily overcome. So, 2 pages together, I can feel the friction between them, but there's not a lot of it. However, if I multiply that effect by as many times as there are pages in these directions, let's see what happens. I'm going to interleave them page by page. 1, 2.
Skin friction is one of the factors that keep the Burj Al Arab standing tall. Mind you, I think they built the hotel in less time than it's taking me to do this.
1,407, 1,408. There we go. All done. Now, according to the theory, the effects of skin friction should have been magnified by as many times as there are interfaces between the pages that I've interleaved. It took a while. I didn't have much else on this afternoon. The only thing is, knowing how long it took, I'm reluctant to test it, but I'm going to. How tough is it? I'm pulling as hard as I possibly can. There's no glue. That is just skin friction. There's no way can I pull those apart. I mean, that is... Honestly, I'm trying as hard as I can. No. I need to try harder. OK, this should be more like it. Obviously, skin friction already doing well just to hold this shackle on. Remember, nothing holding these together, just the friction between the pages. Right, lift it, please. How good is skin friction? I mean, really, how good? Up! OK. Time to demonstrate, if nothing else, my faith in science. Yeah, skin friction. That's all that's holding me up, and the weight of that shackle. Remember, no pins in there, no tape, no nails, nothing. Just friction.
And friction is also one of the answers to building on unstable material, even sand. Otherwise, the enormous tower would just topple over. The secret was to use reinforced concrete pile foundations, which are like long nails driven into the ground. They work using skin friction to keep the building in place, even in loose sand.
To show how strong pile foundations can be, a simple demonstration. Jar of uncooked rice and a knife. Put knife into rice. That's something called skin friction in action.
Skin friction is strong enough to support a 320-metre tall tower on sand. There are 9.5 kilometres of concrete piles bored 43 metres into the sand under the hotel to keep it upright and safe. Think of each pile as a page in the directory. Every one makes the bond stronger. Combined, they make the sand as solid as a rock and keep the building standing tall. In Dubai, temperatures can reach a blistering 49 degrees Celsius. And that heat posed a challenge for engineers and architects working with steel.
Metal, like most materials, expands when you heat it up. Think about it. If you've got the lid stuck on a jar, warm it up a bit and the metal lid will expand and you can free it. That's a good thing. But if you're working on giant metal trusses and they're expanding and contracting according to the temperature at different times of day, and you're trying to fit them together in a very precise way, it's going to be tricky.
The Burj Al Arab was constructed using a steel exoskeleton, an external frame. The 6 steel trusses that support the building's weight are up to 85 metres long. That's longer than a jumbo jet. In the desert heat, the lengths of steel could expand by 5 centimetres, which was critical during construction when everything had to come together exactly.
These 2 steel triangles will represent the huge steel trusses on the Burj. And they really are huge, 80 metres long, but the principles will be the same even at this scale. So they've been machined very accurately, so they can be fixed together using these fixings. That goes in there, that mounts in the hole. And one here. So that's my steel structure firmly fixed together. Fine, but it hasn't yet had to cope with the problems of desert heat and the problems of heat expansion associated with it. Could be waiting a while here for some desert heat, but that's okay, we can bring our own. Gas axe, please. Thank you. While he's firing that up, I'm going to remove one of these fixings because I want to see the effect of that thermal expansion. Right. Well, that was, I think we can agree, a hot day. But if I try and put my original fixing back in, line it up, remember this machine so the holes should align, and... oh, surprise, surprise, they don't. There's absolutely no way is that going to go through there because the metal's expanded. The holes ended up in the wrong place.
When the top metal bar undergoes thermal expansion, it becomes longer, but the bottom one stays the same. This means that the holes in each no longer align.
this were 80 times bigger, imagine the effect it would have then. But what can you do about it? The steel trusses are going to grow and shrink, depending upon the time of day and the temperature. That will happen. It could be disastrous. You could end up with the crooked tower. The engineers found an ingenious solution, thanks to the cam of an engine. Cams are used, of course, in car engines. You've probably heard of a camshaft. Well, here is one. This is the top of the engine. This assembly here is to operate the valves, which would be in the cylinder bores below. They have to open and close very quickly to let fuel and air in and exhaust gases out. That's where the cams come in. So I'm going to be the engine turning here. And as I rotate the camshaft, you can see the cams move eccentrically. These lobes where they bulge and stick out. Push down on this assembly here, open the valve, and then shut it. It's a clever principle and one that's been used for a long, long time.
The off-centre bulge of a cam allows it to open and close engine valves on each rotation of the camshaft. The builders of the Burj Al Arab borrowed from that idea to overcome the problems caused by extreme desert heat.
This fixing, it's called an eccentric fixing. It's been designed using, well, the same sort of principle. This is like a cam inside this hole here. And that gives us the flexibility we need to cope with this heat expansion. So let's put it in, line it up roughly in the big hole there. And if I drop that in, we can manoeuvre it around, and there it is. That lines up perfectly. That's the connection between the engine's cam and our fixings for building in the desert.
The eccentric fixing allows the top hole to be moved so that no matter how much the steel expands, it can still be aligned to the bottom hole. Engineers at the hotel, taking their inspiration from engine cams, designed bespoke movable fixings that allowed them to install the massive trusses accurately, despite the thermal expansion. Once installed, everything was welded firmly in place. Now the building expands and contracts as a whole, keeping it in shape. And when the skeleton was complete, it could be covered or clothed, literally. Having the tallest atrium in the world caused a huge headache for the engineers. Make the wall solid, and you have an enormous dark cave. Make one wall out of glass, and you create an enormous oven. The solution lay in making the world's largest cloth wall. But they didn't use any old cloth. They used glass fibre.
So whilst the entire wall allows light through, making the atrium feel bright and airy, it blocks the harshest of the rays and stops them from roasting the guests with heat and blinding them with glare.
Modern glass fibres are strong, light and transparent. The wall is made by spinning thin filaments of glass into fibres and weaving them into a cloth. The cloth allows a small percentage of the sun's energy through, enough to illuminate the room, but not overheat it.
So it really is that beautiful sail that means guests and visitors walk into the atrium and find refuge from the heat and glare of the desert outside. It's an oasis.
In the baking heat of the desert, one of the ultimate luxuries must be a cool, air-conditioned room. Even when temperatures approach 50 Celsius outside, the interior of the Burj Al Arab maintains a balmy 23 degrees. But keeping it this way isn't as simple as you might think.
Creating and maintaining an oasis in the desert presented the engineers with a series of challenges right from the very beginning.
The real problem is managing the big difference between temperatures inside and outside the hotel. On a hot day, the difference between the two can be 20 degrees Celsius. Temperature differences create pressure differences. In nature, big pressure differences create violent winds, even hurricanes. Pressure differences affect all skyscrapers. They're especially bad in a structure the size of the Burj Al Arab in the desert. It could literally stop people getting in and out of the building. Back on home soil, Professor of Building Engineering Physics Doug King explains why combining air conditioning, a tall building and a scorching desert can stack up big trouble.
So these big temperature differences, although they make life nicer inside the building, they can bring big problems.
Absolutely. And we're going to demonstrate that with this model, which is a scale model of the atrium at the Burj.
I did wonder. It's not as big, is it?
No, unfortunately, we couldn't get one that big in here, so we've had to scale things down a bit. We've got a light bulb at the bottom, which is representing the heat gains from people and from the sun shining in through the windows onto the floor. And we've got about 1 kilogram of dry ice on a tray at the top, which is representing the cooling effect of the air conditioning system.
And the problem is all to do with airflow. An air pellet will show how the air circulates. Heat from people and the sun through the windows on the ground floor cause the air to rise. The air conditioning cools it down, making it more dense, and the air falls.
We've got upflow on the one side, and we've got downflow on the other side.
Leaving you with a tall column of cold, heavy air surrounded by the hot desert. Which doesn't sound like a problem.
I still don't see why the big problem.
If the building stays closed, it's not a problem. The problem happens when we've got this big stack of cold air inside, we've got warm air outside, and it's all being held back by the front door. So why don't you open the door and see what happens?
Right, there's a door down here. Open the door and
that's
see.
the one.
OK, so I'll open the door. Ooh, yes.
What's happening now? See how quickly it's clearing down? You've got this big column of cold air inside, which is much heavier than the air outside, and it's all being forced out through that little opening.
So that's on this scale, you can see it's rushing out. That's not just tumbling out because I've opened the door. That's being pushed out.
That's right.
By this pressure
And
difference.
see how quickly all of that air inside the model has fallen down and pushed the air out through the door.
So if that's how it works on this scale, how big a problem does it represent for something the size of Burj Al Arab?
Well, for something as big as that atrium, it's 180 metres high, that's an enormous stack of cold air. Very, very dense at the bottom. Opening that door against that pressure is going to be like trying to lift a sack of potatoes.
To be more precise, the vast atrium at the Burj Al Arab, combined with the heat of the desert outside, could create the equivalent of 21 bags of sugar pressing against the door.
So 21 kilo weight suspended from a pulley. This then is about as tough as it would be to open the door at the Burj Al Arab. I mean, it's not impossible, but it is a bit of a workout. I don't think you want to work out every time you open the door, especially if you've saved up to book a suite.
With the largest atrium in the world, this problem is especially acute for the Burj Al Arab. The unwanted stack effect was first noticed with the rise of the skyscraper. Workers in New York and Chicago complained not only of drafts, but that they couldn't even open the doors of their buildings because of pressure differences inside and outside.
One solution to the problem is to equalize the pressure inside the building with the pressure outside the building. But that would mean you'd need to equalize the temperature in here with the temperature out there in the desert. You wouldn't be able to heat or cool the building. And I think having the temperature in here hover around the 40-degree mark does rather spoil the whole idea of an oasis in the desert. The hotel might lose a star or two for that.
What you need is a means of getting between two areas of different pressure, outside on the street and inside the hotel, without allowing the pressures to equalize.
There was a different solution, and it came from something inspired by a 19th century French coal mine.
In 1839, French mining engineer Jacques Triget overcame the problem of moving between two areas of different pressure in waterlogged coal mines. He created the world's first airlock.
This is how Triget's system worked. This is my waterlogged ground. Well, it's glass, but you know what I mean. Here's my mine shaft. If I just sink a mine shaft into waterlogged ground like this, well, it's just full of water at the bottom. Nobody can work down there. The answer to that, fairly simple. Seal it at the top. That stops the air getting out, which means the water can't get in. That's all well and good until you need to open the top to let your workers go down the mine. Then it floods with water again. The answer to that one: establish your dry mine shaft, fit an airlock at the top, let your workers in, then once they're safely in, seal it behind them. Everything stays dry, everybody's happy. What they needed at the Burj Al Arab was some sort of airlock so they could separate the pressure inside the hotel from the pressure outside. Sounds complicated, like something off a space station. But in fact, I've just been through it. It's a revolving door.
Revolving doors are designed in such a way that there's never a direct opening to the street. The inside is sealed from the outside, even when the door is spinning. First used in Rector's Restaurant in Times Square in New York in 1899, its tagline was "Always open, always closed," because the door keeps a seal even when you go through it. This makes the sort of airlock that's needed to stop the big outrush of air that would happen because of the stack effect. Now everyone who can afford it can come and go in comfort. But comfort can bring its own difficulties.
It's probably not surprising that pretty much every electronic gizmo conceivable has been incorporated into these rooms, all operated by remote control. At the touch of a button, televisions drop down out of the ceiling or pop up out of pieces of furniture. You can change the temperature, open and close the doors, change the mood, adjust the lighting, dim it, make it romantic. Let's leave it bright. So whilst all of this is great for the guests, it can be a bit of a headache for an electrical engineer.
Luxury calls for a lot of energy. Just the lights in one suite can draw more power than all the appliances in a British home burn in a whole day. And making the mood romantic could have shocking consequences.
So to dim the lights, simply press a button. Really not complicated, we're all familiar with dimmers. But simply pressing that button could have had a catastrophic effect.
The origin of the potential problem lies in what happens to an electrical current when you dim the bulb. It can heat the wires to abnormal levels and start a fire. To show what can go wrong when you're adjusting the ambience, we're going to check into my own replica of a luxury hotel room. I've brought electrical expert Paul Mitchison along to create a sophisticated lighting system.
Oh yeah, home from home. No, not back in the Burj Al Arab. This is my replica. There's no ensuite yet, or jacuzzi, or underfloor heating, but it's got a bedside table and plastic roses. Everything the modern luxury bedroom needs, including lights. Yeah, they don't really come on and off when you do that. That's just Paul out there operating them. Still, thank you. There it is, all working perfectly.
My shed may not be a fully authentic replica, but it has two crucial similarities. It has a high-voltage power supply for the electrical systems, and it has a dimming system. Paul, in addition to providing adult supervision, has set up a high-tech monitoring station, complete with a complicated array of gauges and test equipment.
Paul, to me, as a customer staying in my luxury hotel room, I mean, the lights are on, that's it. What actually is going on in there? What's happening?
So at the moment, what we're doing is we have a waveform that we can see here on the oscilloscope, and this is electric current, which is powering the lights.
Yeah.
And at the moment, the key thing to note here really is that this is a very smooth waveform.
So this is what a normal current looks like on an oscilloscope. It's regular and safe.
So a smooth waveform there, all right. But what if I change things a bit? This is what I want to change. That's a luxury bedroom, and I think that light, it's a bit harsh.
You want something a bit more cosy?
Yeah. So I'd like to change the light setting. I'd like to have, instead of 3 on full, I'd like to put 6 lights on, but dim.
Okay, so in that case, what we could do is we could dim those. We could bring up another 3.
It's a much better ambience in there. But just, am I right? That's the same amount of light. We just got 6 lights on, but lower.
That's correct.
So-
Same amount of power into the lights.
We can see from the oscilloscope that something has changed drastically.
So what's different?
The problem is now is that we're delivering power to the lights in short bursts.
So
And
that's how the power's been halved then?
That's exactly right, yes.
Because I always thought it was like, a dimmer was like a tap. Because if you turn a tap on full, and then that's too much, you turn it down halfway, and half the amount of water comes out. And I thought a dimmer was the same. You just turn it down, and half the amount of electricity goes to the lights.
So it's more like turning the tap on and then off, and then on and then off.
Modern dimmer switches basically shut off the power to the light 120 times a second. It has the effect of not letting the light ever achieve full brightness. It also has a side effect.
So it's the same amount of electricity but being switched on and off very quickly.
That's right.
Well,
That's
why is that different? Why does that upset things?
So the problem is that you're only delivering the power for a short period of time. And in order to do that, you introduce extra heating effects in the wires.
An electrical current in a wire always creates a certain amount of heat, but adding a dimmer switch can add extra heat to the wire, sometimes dangerously so. The on-off action of a dimmer switch creates so-called harmonic distortion, a sort of chaotic current in the wires, frequencies the system isn't designed to deal with. A wire heating up doesn't sound too ominous. It might smolder away, but in the wrong circumstances, that wire can ignite flammable items close to it. If, for example, someone had carelessly left the exposed wire on a waste paper basket full of cotton wool, which might happen to be soaked in nail varnish remover, it could happen. With 6 lights on dim, let's see what does happen.
Yeah, my hotel's on fire. Just so you know,
Okay,
that's a lot of heating.
That took less than 20 seconds to catch. You really wouldn't want that in a top-class hotel.
The shed's on fire. You've ruined my hotel quite badly. Yeah, that is. I see your point. That is a potential problem.
Yeah.
Cool, blimey, bloody hell. That's hot.
Obviously, this is a very exaggerated scenario. Electricians don't generally run exposed wires through flammable bins of cotton wool. But if it is a serious threat, how come dimmers are so common? Why isn't there a fire every time someone wants to change the ambiance? That could ruin the mood. It's because of electrical defenses that include part of a camera's flash.
Yeah, I do see your point.
Yeah, it's not great, is it?
No, my hotel's ruined. So clearly, that needs to be avoided, and it is because they have dimmers, and that doesn't happen. So what's the solution?
So the solution is the capacitor that's in the camera flash. So we're all familiar with regular camera.
Early camera flashes used explosive powder to create the bright lights. But carrying that around was not for the faint-hearted. They needed a safe, portable alternative. And the solution came in the form of an electrical component known as a capacitor. In cameras, the capacitor stores up energy and releases it all at once, setting off the flash. But in buildings, combined with inductors, they act like filters, removing the chaotic currents that can cause fires.
This is a regular, relatively large capacitor. So this is the thing that allows you to take energy more slowly and release it back to the lights.
But all that does is it accumulates this energy and then it releases it at a controllable rate and stops
that happening.
burning your shed down.
I wish I'd known that 10 minutes ago. I'd still have a shed. The Burj Al Arab's capacitors are buried deep in the building. With the inductors, they are the unsung electrical heroes that protect the hotel from itself and its pampered guests.
I guess it is a relief to know that when I dim the lights, I'm not going to set fire to the Burj Al Arab. I imagine the bill would be quite big if I did. Yeah, I'd never get that through on expenses.
The designers of this amazing building didn't limit the spectacle just to the structure. It is, after all, a hotel, and the guests will spend most of their time inside looking around, not outside looking in.
When it comes to earning its keep, this building is all about symbolising luxury and opulence. So what could be the best possible luxury here in a hotel perched in a scorching desert of sand and sea?
Yep, fountains. Think about it. A fountain in the desert is the ultimate in opulence. And not just any old fountains, a series of digitally controlled million-pound masterpieces. And whilst fountains are pretty and all that, it takes some surprising engineering to create the flair.
You need to be seen to do something extravagant and opulent with the water. And the water features here are an engineering feat in their own right. Mesmerising. Sometimes the water doesn't even look like water.
That's because it's not behaving like water. Normal water, that is. Normal water can't move like this does. To allow it to play these tricks, you need to eliminate turbulence. It has to achieve an almost unreal glassy smoothness. Something called laminar flow.
Here comes, if you need it, a quick reminder of how water behaves in a flow normally. There it goes. Now that's, well, it's just a mess. That's because of turbulence. There's lots of eddies and flows and swirls in there, which is fine for use here on the farm. But if you want to make those beautiful, polished, glass-like tubes in the fountains at the Burj Al Arab, you need to smooth that flow out. You need to make it laminar. And to do that, the engineers turned to a type of hose used to help put out fires in skyscrapers.
The 1930s, buildings grew taller. Firefighters needed to stream water higher to quench towering infernos. A helpful hydraulic engineer realized that turbulence reduced the range of fire hoses because the water flow broke up in air. His invention to smooth out the flow in fire hoses to make it more laminar was the key to the Burj Al Arab's glassy fountains.
Right, quick quiet minute before we do the next bit, and we are going to be finding out about this laminar flow business, which, as far as I can understand, is all about doing, well, what seems impossible. Here's an example, my coffee. Don't worry, they'll get a coffee too once they've earned it. If I stir in the milk, there we go. Stir it all in. There you go. It's all mixed up thoroughly. Wouldn't it be kind of cool if we could unstir it and then be sort of left with a blob of milk and black coffee? So maybe if I stir the other way and... well, no, obviously you can't. That would be turning back time.
We haven't yet conquered time travel, and you can't unstir coffee unless you can make water behave in a fully laminar way. Amazingly, however, you can unstir some liquids. Professor Tom Mullen from Manchester University, an expert in fluid dynamics, shows me how.
So, Tom, with this device, I'm not sure we're about to spin a salad or do some painting. And what's this got to do with laminar flow, whatever that is, and trying to unstir my coffee? That's your mission, to explain all of that.
Oh. Well, what you have to do is put these coloured dye into the fluid, and then we'll stir it around and see what happens.
All right.
The liquid inside is thick, viscous sugar syrup.
Yeah, a bit further along here, this direction.
Right.
And the coloured blobs are the same stuff with food dye added.
OK, that's fine.
So 3 blobs, good, not much flowing, laminar or otherwise going on right now.
Now we have to create the flow, and so to create the flow, what we're going to do is turn that handle, say, 5 times in that direction.
Right, so that's
fine.
It's quite thick stuff, this, isn't it? 1,
It's very sticky fluid.
2,
Keep going.
3, 4, 5. OK, I've done that.
Now it looks like we've created a right mess.
It's a mess, yes. It's all gone.
What we need to do, or what you'd like to do, is go backwards the same number of turns.
So I'm
5
literally
turns.
unstirring it.
Unstir.
I feel
Your
like
coffee.
somebody might be having a laugh at my expense. 1, 2, 3, 4.
Slow down a bit. Just keep going slowly a bit. Slow it down, slow it down, slow it down. And there you have
Look at that!
your 3 bobs back again.
I've literally unstirred it. That's a great party trick.
Thick, viscous liquids like sugar syrup are very smooth. It's easy to make them move in a laminar way. They don't behave turbulently like water, so you can unstir them and make the blobs reappear. If water behaved like that, you could unstir your coffee. To make water flow in a laminar fashion, you need to remove the turbulence with a laminar flow nozzle.
Well, the good news immediately is, now correct me if I'm wrong, this would appear to be laminar flow in water.
This is laminar flow that's coming out of this nozzle here, whereas this is turbulent flow. The reason you can tell immediately it's turbulent is because you can see it. It scatters the light. And in this case, it's nice and glassy smooth, and it's laminar.
OK, so quite a simple difference, really. Neat, tidy and elegant, scruffy and a mess. But to achieve this, it needs this device here that looks like something out of a 60s sci-fi movie. What is it?
You have turbulent flow coming in, and then what happens is the flow goes through these gauzes, through these straws and so on, and so the turbulence decays as it comes through here, and you end up with laminar flow coming out of the nozzle.
The gauze and straws effectively smooth the water, removing the bubbles and swirls that cause turbulence. Non-turbulent water can flow quicker and more smoothly.
So to solve the problem then, of fast-moving laminar flow in water for the Burj Al Arab's fountains, what you need is a device like this to calm the water down.
Yes.
And smoothly flowing water also helped firefighters. In the 30s, American engineer Horace Barker had a brainwave. He realized that removing turbulence made the water travel further. His new fire hose design had metal feathers inside that aligned the water as it left, reducing this turbulence. Barker's flow straightener extended the range of fire hoses. The smooth water flow traveled further, so firefighters could tackle blazes on the higher floors of skyscrapers more easily. Laminar flow nozzles go one step further than Barker's device, removing all turbulence and smoothing the water to a glassy finish. The fountains at the Burj Al Arab incorporate 66 laminar flow nozzles. Pretty sure theirs aren't made from drinking straws, though. Either way, they allow for breathtaking displays. You see, the crucial thing about the Burj Al Arab is that it's all about the bling. It's engineering to impress, not just to survive. All these engineering achievements have made the Burj Al Arab a spectacular feature on Dubai's skyline.
The Burj Al Arab instantly joined the world's list of iconic landmarks, becoming the face of Dubai, synonymous with its reinvention as a luxury playground. Behind the glitz, the glamour and the spectacular show, there is some amazing and solid engineering.
And none of it would have been possible without a game of jacks, an engine cam, the pages of a phone book, a revolution in fire hose design, and a camera flash.
You ruined my hotel, man.